me about it.
So basically, the Atlas download server was compromised, and they put malware on top of the CCleaner app, which is supposed to get malware off the computer. And since it had a certificate by Atlas, it had a free pass basically from any antivirus. And so whenever you downloaded CCleaner, you downloaded malware as well.
What did the malware do?
It's just a botnet. It's nothing like bad. But
how did they get a certificate? Anyone? Yeah, shoot.
It wasn't just like a malware that was bundled along with the application. They actually got into the build process, and CCleaner itself was the malware and was infected. It wasn't just the installer. It was actually the binary file of CCleaner. And they've released the hashes to check for, but Talos found what the malware was calling home to, and no one had bought the domains, so they turned them into a sinkhole. So they don't think anything bad has happened because.
So there's three different things going on in this story, as far as I understand. So first of all, there's what we call the supply chain attack, right, where somebody has basically gotten a piece, as far as I understand, I may be wrong about this, but a piece of software that is used in building another piece of software. They've actually substituted this somehow with something infected, and that got rolled into another product which was widely distributed. So these are actually starting to be a big deal. Why are they a big deal? Well, because a lot of software packages that people use are not, very well monitored. A lot of them are open source. Sometimes you download things from relatively untrusted sites. Those can be compromised and so on. So this is like the new hotness of attacking people is getting in at a higher level rather than compromising their stuff. Yes.
So again, because later, a similar attack happened with the Python package.
Yes, so there's been a bunch of these recently, and there will probably be more. Okay, so there's a supply chain attack. Now somebody mentioned a certificate, a signing certificate. What kind is that? What kind of certificate? Can somebody tell me more explicitly what kind of certificate are we talking about? What does it do? I'm still not 100% sure about every detail of this attack. I just saw it briefly this morning, so feel free to contribute details. What do these certificates do? When I say there's a certificate, and I'm talking about a piece of code, well, where do we use certificates on the internet? Where do these things show up?
Usually for websites to show that they're actually authentic websites.
Good. Okay, so one place we use certificates, and we'll talk about those more in a little bit, is we use them to generally certificates are used as part of the process of authenticating things. So we need to give somebody our key, our public key to authenticate something, and we do that in a certificate. It's just a file. So somebody mentioned these are used to authenticate websites. That is very true. This doesn't seem, at least as far as I understand the attack, to have been a web SSL TLS certificate. What kind of certificate was it? Yeah.
Digital certificate. So
it's definitely a digital certificate. What kind?
It's like a hall pass, I guess. It's for computables, and so antiviruses won't necessarily go through it. It's basically telling your computer this is what you just downloaded is safe.
Good. Okay. So what is it that is going to be certified?
Software integrity.
Software. Good. Okay. It's a code signing certificate. It sounds like. So code signing certificates were introduced years ago. Microsoft uses them. Lots of other systems have started to use them. Every iPhone app is signed. And the idea of these certificates, right? So I want to put a piece of code onto your computer. Maybe it's a driver. Maybe it's something else. And I want to sign that piece of code to prove that I actually made it. But who am I? I'm just some software developer, right? So how do we prove that I am a trusted software developer? Who certifies me? Yes.
For example, on the iPhone, you're like, hey, Apple, I'm the person who developed this software, and then Apple is like, hey, this software is legitimate,
Good.
And you trust Apple, and Apple figures out.
Good. In Apple, I actually have to submit my software, and they will only sign it after they've looked at it. But other systems don't require, like Microsoft, doesn't require you to submit every driver that you develop to Microsoft for inspection. They will trust you a little bit more. So they'll actually give me, as a driver manufacturer, a code signing key, because they'll say, you're legit, we've checked you out, you're not going to put malware on people's computer, here's your code signing key. And you could just sign everything you do, because basically I'm a company that is trusted by Microsoft. And once I have such a code signing key, I can sign all my code. And that indicates to the world, I get a certificate from Microsoft, it indicates to the world that this code is legit, or at least made by me. And Microsoft signs its own code and so on. So I don't know whose certificate or whose code signing key was used to sign this thing. Was it Avast?
Symantec.
Symantec. How do they get a Symantec code signing key? Okay, so we got another thing. So we've got this certificate, and we've got code, signing key. Where was it? How was it stolen? We don't actually know the answer, but Symantec seems to have screwed up in some way. And so there are lots of things going on. So we've got like really sophisticated attackers. So we're doing all this stuff. Yes?
Now, so two things. I mean, Chrome is turning off accepting Symantec's certificates soon.
But that's on the web, yes.
Right. Also, wasn't Symantec behind, or wasn't Symantec software required for the 2014 Iran attacks?
I don't know, maybe? Yeah.
What's Symantec?
Symantec is a giant company that buys up other companies and screws them up, basically. And that's kind of what they do. But actually, their real business, if you want to get down to it, or at least their original business, was to be a certificate authority. What's a certificate authority? Who are these people? What do they do?
Like a third party who you would trust to say that this certificate is valid. So usually you'll have something like a certificate chain where each certificate is signed by a certifying authority, which leads back to a root authority who's, the big deal like VeriSign or something like that.
Good. Okay, so we are going to get into public key crypto in the next few days, but before we get into all those details, roughly speaking, on the internet, nobody knows if you're a dog, right? So if I'm some company, I start up a company called Nuco, and I say, I'm legit, trust my software. You guys have no way of knowing if I'm actually a company or if I'm just some malware provider. So we rely on these higher level people, i.e. or e.g. Symantec, to be what we call certification or certificate authorities. And these guys' job, there's a few of them, and they are either trusted by your browser if it's a web certificate, or trusted by your operating system if it's a piece of software. And these guys' job is basically to go out, Nuco comes along and says, no, really, I'm a real company, I'm going to prove this to you somehow. And Symantec says, okay, Nuco, I've checked you out, I think you're legit. Here is a certificate for Nuco, and it embeds Nuco's public key, I believe them. And they do something called digitally signing it. We'll talk more about that later. Signed by Symantec. Okay, and so the question now is, how did somebody who is not legit get a certificate signed by Symantec? Well, they could have defrauded Symantec and claimed to be somebody else. They could have hacked into another company. They could have hacked directly into Symantec. All these things are bad, and they're not supposed to happen because they break the whole security model. So this seems like a kind of on multiple levels, really, really bad thing. Although on the bright side, it seems like it was stopped. Last question. So somebody said a botnet, and they mentioned the word sinkhole. I was hoping somebody could quickly explain what this all means. Anyone? Okay, yeah, go ahead.
So a botnet, it infects your computer, but it doesn't do really anything. It doesn't like delete all your files or corrupt your OS or anything. It just sits and pings a server's like, hey, is there anything happening? Do I need to do anything? And a sinkhole is to say if it's pinging a web address, you grab that web address.
You being a good guy.
Yeah, a good guy grabs that web address and routes them into DevNull, and they just sit there waiting for communication that's never going to come.
Good. So if your computer gets malware on it, gets turned into a bot, you may not even know this. It has to connect up to some centralized service for command and control. People have done clever things like use Twitter or whatever for this, but most of the time people just register some big random looking domain name, and then your botnets connect to that, and then they will, hopefully you'll be able as a bad guy to send commands down to all these computers to do different stuff for you. And so sometimes malware researchers get there ahead of time, and they're able to grab these domains before the botnet people even register them or get their act together. This happened with WannaCry, right? WannaCry, here was a domain that was actually captured by a bunch of malware researchers, and they registered it. And the really interesting thing about that is they got two things. They got a sinkhole, which all of these bots were trying to connect to, so it told them whenever a computer was infected, and they could count the number of computers. And the other thing it did is it just, as a very lucky consequence of the way that particular worm was developed, it turns out if you register that domain, the malware would stop the infection process before it continued. So just by checking that domain and having it registered, the malware would just die. And so it was just a very lucky thing in that case. The sinkhole actually killed the malware instead of just disrupting command and control. But anyway, it seems to me like this is just another example of this kind of thing happening. Yeah.
There's something I read that I didn't really understand. It was domain generator algorithm.
Good. So which domain? You're a bad guy. You want to create a botnet. and you're going to have it connect to some domain on the internet. What are you going to name your domain? Symantec.com? Like, what are you going to name it? Remember, you want your domain to be something kind of, or, random and hard to find, right? So you just pick a random long string, .com, and register it. Now that's great, but what happens when the US government comes along and like seizes .com to shut down your command and control network? Or maybe the domain registrars get ahead of you and they kill it. So what are you going to do? You're going to have your bot, your smart bot, actually generate a series of domains. You're going to want that to be deterministic because your bots are going to basically have to know, maybe these each last for a day, .com, some other .com, and it will just generate a sequence of these things. And that's a domain generator. And the idea is that you can register these things as you go, and the bot will connect there, but people who at least haven't really looked deep into the malware won't know what the next one you're going to register is. So even if they seize one, it only hurts you for a day. Yeah?
Wouldn't it be easier to just use Tor?
Tor is definitely something people have tried to use, but botnets get big, and Tor really sucks. It really turns out that sometimes Tor doesn't have a lot of bandwidth, but people have tried to do this. But a lot of the time, it's just easier to use this kind of hacky stuff. So this is what domain generators do. A lot of the time, what malware researchers do, and it's an interesting job, is they get the malware, they tear it apart, they find the domain generator code, it has to be deterministic, and they wind it forward to predict all the future domains it's going to get, which could be thousands of them. And they go out and they register all those. So this is an arms race. It's not always perfect. Yeah.
Now, does the cost get expensive for the malware, like the bad actors?
Researchers?
The bad actors.
It can, but if you're making more than $7 a day on your malware, it's okay, because that's about what it costs to register a domain every day. So for the malware researchers, it gets a little expensive, maybe to do 1,000 of them in one go, but you get 1,000 days out of that, so it's not bad.
Can you predict these domain names are generated using some entropy techniques or something like,
They have to be somewhat deterministic. There has to be something coded into the malware that predicts where they're going to go. And so, unfortunately, you can't really make it random. It's just, it has to be pseudo-random typically, but that's more detail we get into right here. Okay? Good. Any other interesting news going on? That is not this particular piece of malware.
There's a Pirate Bay, and apparently sometimes when users log into some pages on Pirate Bay, like it runs JavaScript that basically uses the person using on the site, it uses it for like mining.
Yes. So you can make money by mining cryptocurrency in JavaScript. Does it make a lot of money?
I haven't gone through the report in detail, but yeah, just this all I could like.
I think it's actually a pretty good solution, don't you? Right? Like if the choice is pay for advertising or have like excess cycles on your computer, like mining cryptocurrency for Pirate Bay, and you like Pirate Bay, that seems okay to me. But people are freaked out about this for some reason. I don't actually know why. Yeah.
It probably wastes fewer cycles than advertisements and checking in with
Yeah.
advertisers.
Advertising sucks anyway, so yeah, I mean it's probably true.
Yeah.
Okay. So yeah, this is a thing that's happening. Good. Okay. All right. Any quick assignment notices. Okay, guys, you got assignment 1 in, I'm assuming, or you are hopefully really close to getting assignment 1 in. We just wanted to relay some news from the TAs. They are kind of triaging the assignments. Now you notice on the assignment I gave you this very explicit interface for how you were supposed to put inputs in and what they were supposed to how they were supposed to come out. I didn't do this to be a jerk. I did this because we wanted to make the initial pass of grading very easy for the TAs. In other words, the hope was they would be able to write a script that like handed you a ciphertext file according to this interface, got the output, and checked to see if it was actually right. Sadly, this dream, this vision of ours, has not exactly 100% come true for a variety of reasons, one of which is that some of you guys did not follow the specification. Sometimes, like we said, output to standard out, but then you guys wrote to a file, things like that. So it's cool. This is the first assignment. There are going to be some growing pains. It's okay. But you may get a note from the TAs in the next couple of days or next day or so, if you're one of those people, saying, please fix it. And the idea then is, please fix it. And we're going to diff your code. So don't try to fix other things like, oh, I found a great improvement to my algorithm. Don't do that, because that will be a big problem. Yes?
What's for the system, like how you organize the files and everything?
Yeah.
Like, I know I did this and a couple other people did this, like a separate folder for every single
Yeah.
like program. Is that, like, I guess it just wasn't
We
clear
will
enough.
get you some guidance about that, because Alicia, who is currently the head TA grading all the assignments, had some thoughts about this and wanted to like give you guys some like, here's how I would like you to turn it in. I don't have it today, but we're going to get you that before you have to turn, like a few days before you turn the next assignment, just to make life easy for everybody. But in the future, there are going to be no points lost for this, but in the future, there will be points lost for it, so like on assignment 2, make it work. Okay, good. All right, what else? Oh yeah, assignment 2, by the way. Part of it is out on Blackboard, on the GitHub. I meant to get it out last night, it came out this morning. Get started on it, but there's going to be a part 2 that is actually bigger, and that's going to come out in the next day or 2. Just working on making sure the harness works and everything. So that will be out. The due date is 2 weeks from tonight. Good. And part 2 may be a little later. You may get us like a few more days on turning that in. We'll figure it out. Good. Okay. So we were last time. I think we have just gotten, sadly, at this stage of the course, all the way to CBC mode encryption, right? So recall, we started with this notion of a block cipher, which is really useful in the sense that it is a kind of a deterministic function, actually 2 functions, one that enciphers, one that deciphers, takes in a key, takes in a block of text, plain text, spits out a block of ciphertext. And then we pointed out that this notion, which I defined a couple of classes ago or whatever, of, I'm about to spell semantic the wrong way, semantic security. And by the way, this is also equivalently called the following: indistinguishability under chosen plain text attack. These 2 terms are equivalent. This semantic security thing, and if you remember that game we played where I said, okay, you have this challenger, you're an adversary, and you get to encrypt any plain text you want, go for it, and then you get to pick 2 plain text of the same length as challenge and send them in and get back one of them at random, chosen, encrypted under the key. And you, the scheme was secure if no adversary could predict could guess which of those 2 ciphertexts had been encrypted with probability greater than what?
1/2.
Good, okay. And we said that block ciphers all by themselves clearly could not satisfy this definition of indistinguishability under chosen plain text attack, and why? Yes? They're deterministic, right. There's a trivial attack on any deterministic scheme where you just pick the messages M0 and M1, you get encrypted copies of them, you submit those same messages as your challenge messages, you get one of them encrypted back, and you say, I already know what the ciphertext for those things look like, compare, and win the game 100% of the time. So any deterministic encryption scheme cannot possibly satisfy this indistinguishability or semantic security notion. Cannot, right? So this is a big, big deal. But we also observed that randomization of ciphertext might be able to fix this. This is called probabilistic, I'm sorry, I can't bother to spell it out, probabilistic encryption, where every ciphertext has some unique new randomness in it, not necessarily unique, but randomness in it, might not be vulnerable to this attack. And we haven't proved that, but we're going to give some examples of probabilistic encryption schemes that are built from block ciphers, and I'm going to claim to you that they actually will, but we'll get to the details a little later in the course. And the first one we started talking about is this thing called CBC mode, which stands for, anyone remember? Cipher block chaining. Now we've pointed out that CBC mode has a few features that are nice. First of all, it works over multiple blocks of data. So if your data is 30 blocks long, CBC mode is cool with that. In fact, it actually binds together the blocks in a way that prevents patterns from flowing through. Second thing we noticed is it has this additional field that is not in a normal block cipher. Beyond the key, the encryption algorithm, it generates this thing called an initialization vector. And how is it generated? Randomly. Good. It is a random string that is as long as the block length of the cipher. Fantastic. And when we do CBC mode encryption, the very first thing we do is we take the first block of the plain text message, we XOR it with that random initialization vector, which looks a lot like a one-time pad encryption, as it happens. Then we feed the result through the block cipher encryption or encipherment algorithm to get a ciphertext. Fantastic. This really randomizes the first block. How do we carry that randomization forward to the next block? Well, our assumption is this ciphertext, this first ciphertext block, having been effectively randomized, we can use this as essentially the initialization vector for the second block of encryption. So we use the ciphertext block and we XOR that into the second plaintext block, and we rinse and we repeat. Our assumption here is that the plain text is an even multiple of the cipher's block size. If it's not, let's pad it, but let's just say that, okay? Ciphertext, cipher blockchain. We also pointed out that we can decrypt this. Hopefully you guys can work it out, but the decryption algorithm just involves using a decipher operation and then doing some XORs, and it works. Now, people asked me at the end of the class, should the ID be secret, or can we reveal it as part of the message, the ciphertext we're going to send over the wire? What was the answer to that question? The initialization vector, yeah.
That's public, we have to give that out.
We have to give it out. We're not going to try to keep it secret. If anyone tells you keep your IVs secret, they're stupid, don't listen to them. We want the initialization vector to be given to the person who's decrypting it because they need it in order to decrypt at least this very first block. Right? So it's part. We're going to just, in general, in this class, we're going to say that a CBC ciphertext includes the IV. It will be IV C1 ... CN. That will be a ciphertext in CBC mode. We're going to include that. Great. What are the advantages and disadvantages from a purely performance perspective of CBC mode encryption? What do you notice about the encryption algorithm if you want to speed things up? How do we generally speed things up? Yeah.
Well, it can't be parallelized.
It can't be parallelized because in order to encrypt block n, you have to know the encipherment of block n-1. So it's fundamentally, at least in this case, a serial process, one block at a time. Is that true for the decryption algorithm? Can decryption be parallelized?
Yes. Yes.
Yes, it can, because decryption does not, you actually are going to feed the ciphertext blocks in, so you don't have to decrypt. It just happens that decryption is not fundamentally serial, the same way encryption. So these are some differences. What we made an assumption that the initialization vector was random. Okay, so there's one initialization vector for each message, and messages can be arbitrarily long, but there's one initialization vector. What happens if the encryption vector is not random? In fact, what happens if we fix a specific initialization vector, hard-coded, for all messages? What happens to the scheme? Yes?
It becomes the same as a regular block cipher.
Good. It becomes a deterministic block cipher. It's not quite as bad as all that. Because it turns out that one of the neat features of CBC is if there's some entropy in each plaintext block, then that gets carried forward into the message as well. So, but the first block will certainly be deterministic based on the first plaintext block, and everything will be subsequently deterministic. But at least you might get some entropy from the message, but it's pretty bad. So do we use fixed IVs? Let me see if I actually say this up here. Before I get to this right here, I'm going to show you a picture. This is from a standard. It's a few years old. It's called the AACS standard. It is the encryption standard used. It's an early draft of the encryption standard used to encrypt Blu-ray discs. Okay, what it says is, unless otherwise specified, the initialization vector used at the beginning of a CBC encryption or decryption chain is a constant ID0, which is blah. Okay, so people, real people out in the world, constantly misuse CBC mode by doing crap like this. This is not what you're supposed to do. In fact, they actually eventually fixed this, but at some point, like, this is an example of people doing this. So you basically fall back to a deterministic cipher if you misuse CBC. Okay, so the question we should be asking is CBC a secure encryption scheme? And by secure, I mean, does it meet this definition of semantic security? And the answer I'm going to give you, which for now I'm going to say trust me, is yes. If the block cipher is secure, meaning it's a pseudo-random permutation, not very important, and you pick your IVs correctly, meaning they're actually random, we can actually prove that under the assumption of a secure block cipher, the resulting scheme actually satisfies this definition, as long as the two challenge messages are equal length. And the proof appears in this paper by Bellari, Desai, Giacomo, and Rague. I can never pronounce his name. But of course, people screw this up all the time. So that means in practice, you might get it wrong.
Professor, just making sure I understand correctly, the idea is to use a different ID on each transmission?
Yes. A message, by the way, should be, remember, you have a message which may be multiple blocks long. So I just want to separate this idea of a block of the message, which is one, from a larger message. But yes, a unique random ID. I mean, remember, random doesn't actually mean unique, but with high probability.
Right, sure.
Yeah. Yes?
How does that differ since you're just going to give the ID out to people? So you're not going to make it secret, then?
It's a good question. I mean, so what is the secret?
the key?
Yes.
Yeah, but I mean, if you're just gonna give people the IV, what does it matter whether it's random or fixed?
Well, okay, so remember the semantic security game. So the first question is, if the IV is fixed, will the scheme satisfy the semantic security game? Right? Remember the claim we made was there's an attack that works for any deterministic encryption algorithm. So if we implement CBC mode using a fixed hard-coded IV, and every message gets that same IV, it will be deterministic, so it will clearly fail. Okay, my claim, which again I'm not going to support in a lot of detail right now, is that once you have a random IV, this no longer works. And the reason is, think about it this way. Let me actually spell it out. So let's say in the first phase of the game, I pick M0, and I send that to get the encryption of M0. Remember, I am allowed to ask for this. Okay, so encrypt M0 would be equal to, let's call this IV1 XORed, let's see if I can find room, with, let's just say it's a one block message to make our life simple, XORed with M0. And we would feed that into the encipherment portion of the cipher with key K. Okay, so this would be the first ciphertext we got back, so let's call this C0. All right. Now at the challenge phase, I'm going to feed M0 and M1 in as my challenge ciphertext, but this time they're going to be encrypted with a different IV. I'm going to be given the IV, but they're going to be encrypted with a different IV. Actually, let's put the IV1 as an explicit aspect of this message. And then we'll call this C0 prime. So the second time I get the encryption of that message, it will look slightly different. Even though it is the same message, it will be IV2 XORed with M0, and IV2 will be given to me. Now the question is, if you as an adversary are given these two different encryptions of the same message, but two different ciphertexts, can you link them together in some way? I'm not going to go into a full proof, but let's just look at it intuitively. IV1 and IV2 are two different random numbers. Is there anything you can link there? No, clearly just random numbers. Okay, now the question is, can we link together these encipherments, even though they have the same message? And I'm going to claim to you intuitively that if these things are themselves random, the IV1 and IV2, what we're kind of doing is we're basically turning the XOR of IV1 with M0 is essentially kind of a one-time pad encryption. It's not really quite fair because we're giving out the IV. But we're then feeding that into the encipher algorithm. And so the point is, two different values are going to go into the encipherment algorithm here. And the property of a block cipher, and I hope just intuitively you get this, if I encipher two different messages with a secret key, can you learn much about from the resulting outputs, can you learn much about the inputs if the block cipher is secure? What can you learn? It's a pseudo-random permutation, meaning that the outputs are indistinguishable from the outputs of a random permutation. And we've already kind of stated that a random permutation is a permutation sampled from like every possible permutation randomly. And intuitively what that means is that with the very limited exception that two different values can't produce the same output, effectively the outputs are very, very hard. They're very close to random outputs. They would be sort of indistinguishable from random noise. And so right now, before I go into a full proof of this, which I don't want to do now, I'm going to claim to you that as long as I don't actually encipher the same value, the resulting outputs will essentially look like unlinkable junk. And that's the intuition, not the proof, just the intuition for why CBC mode works. And the same kind of thing, once you kind of accept that intuition, it works for every block of the message because of this feedback loop. I know that's not super satisfying. It's all I'm going to cover for now, because we will talk about it. Yes?
Could you just increment the IV, or does it need to be random?
Good question. Let's ask that question. Let's say I just increment the IV. So, what I do is I start with a random IV, the first message. The second message, I use that same IV plus 1. Is that a secure, semantically secure encryption scheme? I love it. Thank you for teeing this up. Let's see. Okay, so let me just draw this out. Let's again assume a one block message just to make our life simple. So our initial IV, we'll just call that IV. And the first ciphertext that I encrypt will look like IV XOR M0 sent through the block cipher with the key, okay? And the second ciphertext that the challenger encrypts will be enc K of IV plus 1, that's literally a plus, XORed with M0. And so on, IV plus N XOR M0. Does anyone see a strategy by which an attacker can win the semantic security game using this approach? Yeah?
If you repeat the same message for your channel, you're going to see cascading. You're going to see like one bit at a time change, cascading bits. It'll work like that.
So I claim that the fact that a single bit changes in the IV, like or what goes into the cipher, I'm just going to claim to you now that if the thing that actually goes into the block cipher is different, even by a single bit, it's going to look very different on the output. The block cipher really trashes its output. Yes?
If you subtract 1 from the message.
Ah, very good. So I'm an attacker. I know in advance that this challenger is going to use a specific IV, meaning the last IV they gave me, plus 1. And obviously that means I can't just resubmit. My earlier strategy when I was trying to attack the deterministic version of this thing was to submit M0 in the first challenge, and then submit M0, M1 as my challenge messages. That worked great when it was deterministic. Now the IV is changing, and the question you're asking is it still possible for me to adjust the messages I submit so that at the end of the day, even though the IV changed, it changed in a predictable way so that when you XOR that IV with the message I send, it will go back. I can undo the increment that's happening to the IV. And the answer is exactly what you said. So let's say I want to submit the same message and have it be deterministic again. Well, I know that the attacker is going to use the previous IV plus 1, so I can just submit the message M0 minus 1. And maybe this doesn't always work with XOR, but let's just say that the bit is just like the low order bit being flipped. In many cases, if the IV is like even, what I can do is I can basically adjust M0 so that these two things are equal. And if these two things, the inputs are equal, then the ciphertext outputs will be equal. And now I can run a strategy that actually attacks CBC mode. So again, if you didn't follow every single aspect of this, that's fine. It'll be something you will probably have to remember, figure out yourself later. But these attacks do work if I... Uh-oh, is that North Korea coming, or is that...
Shelter in place. Ordered 1 mile radius of 3400 Fairfield Road, Curtis Bay, including 21060, 21255, 21226.
That's not us, right?
No, it's
Okay.
Can you see how far it is from like the water? It's like 27 miles away.
Okay, yeah, all right. That is a really annoying look. Okay, good.
Why are we sheltering?
All right, moving on. Since we're not sheltering in place, or we are sheltering in place. Okay, so moving on. The basic gist of what I want you to get about CBC mode is that the IV has to be unpredictable. If the adversary can predict what the next IV is going to be, then in general they can adjust the message they send in to like basically remove that IV or to adjust their message so that this attack works. So we want unpredictable IVs. Random IVs are unpredictable, but they must be randomly chosen after the attacker picks their message. They can't be chosen before. There are actually real attacks we're going to run into that matter here. So we'll come back to this one. Good. Okay, so I want you to believe that if you do everything right in CBC mode, it's secure. Let's try another mode. There are actually a number of different ways to use block ciphers. Let's try another one. The next one we're going to talk about is actually really interesting because it's qualitatively different than CBC mode. So what we're going to use, what we're going to do, now I may have mentioned this earlier, there's a thing called a stream cipher. A stream cipher is basically a cipher where instead of encrypting blocks at a time, we can encrypt individual bits. And we can do this in a way where there's kind of a state that updates. Okay? So when we use block ciphers, we can actually turn a block cipher into a stream cipher as follows. Okay, the first thing we do is actually before I get this, let's go back to the one-time pad. Remember the one-time pad, what was the one-time pad? If I had a message that looked like P1, P2, P3, let's say these are each 128 bits long, and I want to encrypt them with a one-time pad, what do I do?
K1, K2, K3.
Good, I generate 3 completely random keys of the same length, K1, K2, K3, and I XOR. And the problem we had with doing that was what? What was the functional, not like a security problem, it works great, it's unbreakable. What was the actual problem in terms of deployment that we had with using one-time pads?
Key distribution. Just one-time usage of the key. And
yeah, we have to generate a lot of key material and ship it all over the place. Okay, now let's say we want to compress those keys into something much smaller. So when I encrypt 1,000,000 blocks of messages, I don't have to ship you 1,000,000 blocks of key. I can just ship you one short 128-bit AES key. Well, it turns out that AES, or any block cipher, is a really convenient way of doing that kind of compression. And the way we do it is using something called counter mode. The basic idea is the following. Instead of actually using random keys, what I'm going to do, I'm still going to XOR, the basic structure is the same, but instead of generating my keys randomly, I'm going to encipher an input value using the secret key that is an integer, expressed as a block, right? So I'm going to take a series of 0 bits, that's going to be my input to the block cipher, I'm going to generate this, and then I'm going to XOR that with a plaintext block. And what am I going to do for the next message? The name of this mode should be a very strong hint about what we're going to do. We're just going to increment the key, so this is going to be the encryption of the integer 1, and so on. Okay? Now this is slightly different than what's on the board, and I'll explain that in a second. So just using this idea of enciphering different values, turns out that what we're really doing is we're building a key stream for something that looks a lot like a one-time pad. Now, intuitively, why do you think this approach might be secure?
Because the encryption totally trashes the, and
Express it to me in terms of the one-time pad. We know something about the one-time pad security, right? Which is if X, then Y. Express the one-time pad security in terms of if X, then Y. Yes?
The key is completely random.
Then we get a unbreakable cipher. Okay? And I will claim to you that the one-time pad with a completely random key for each message will satisfy semantic security because it's unbreakable. But here we don't have a completely random key, do we? We have this kind of weirdly algorithmically generated string of bits. It's clearly not random. Anything but random. So what now? How do we make a claim that the one-time pad security is somehow linked to this thing? Yes?
If no information about the P1 leaks out, then the fact that if they have no information of P1 leaks out, which is what we've been assuming, then the P2, which there's no way of telling, there's no information leaking out from the P messages.
But that doesn't really link things back to the one-time pad. Okay, so we know the one-time pad would be secure with a random key. This is not a random key. Yes?
Because you're never going to repeat the same key if you implement it?
Yeah, well here I've actually kind of made a, not a great solution. I've started with 0, and I'm assuming that if I start encrypting another message, I'm not going to restart with 0, because that would not work. Okay, but I'm always going to increment, so I'm always going to hold on to this state. But say what you were saying. I'm never going to repeat an input to the cipher. Yes.
Right. Which means that it's like pseudo-random, so you can't really tell.
I like that word pseudo-random. Now, what does pseudo-random mean?
It looks random.
Good, good. It actually has a really formal meaning. In cryptography, pseudo-random means indistinguishable to a computationally limited attacker, indistinguishable from random. And that's a powerful concept. Think about this. I know that if this stuff is random, this is an unbreakable cipher. Okay? It's not random. But to every computationally limited attacker, I'm going to tell you, as a fact, that this is going to be indistinguishable from random. Now, prove to me by contradiction that the resulting cipher is secure. Here is how I would do it. Okay, so I know that this thing, I've been given the fact that this stream of bits that we're XORing with is indistinguishable from random. That is a fact I can start with. I know that one-time pads are perfectly secure. Good, that's another fact I can start with. All right, let's give this resulting ciphertext to an attacker, a computationally limited attacker, and have it break it in some way for any definition of break. If he succeeds, what does that imply? One of two things. Yes, we'll shoot. Somebody else, mix it up. Yeah.
Block cipher is not pseudo-random.
Good. It implies that literally either the one-time pad itself with perfectly random key is not secure, which we have already proved is not true, or it implies that somehow he's distinguishing these pseudo-random bits from random bits, because if he can break it, he clearly can never break it when it's a one-time pad. If he's breaking it with any reasonable probability when it's these bits, then that means we have built a distinguisher that can tell the difference between pure random bits and pseudo-random bits. So basically, the minute we say these are pseudo-random bits, we're saying that there is no attacker that can break it with computationally limited attacker with significantly higher probability than a one-time pad. Yes?
And what about cases where there's a known pseudo-random number generator and you have a string of numbers from that generator which you might be able to use to distinguish which generator is where it is in its cycle?
Okay, so let's take this. We are actually we're using AES with a random key to generate a string of random bits. Okay, so how do you attack this? Forget, you're not computationally limited anymore. You can run forever. What's your basic attack? How do you distinguish those bits from random? Forget about breaking the cipher. How do you distinguish those bits from random? I'm going to let you run forever. You can run for 2 to the 128 operations if you want. How do you? Yeah, you can do a brute force attack, right? So let's say that I was to give you this string of bits, which is 3 blocks long, okay, and I claim to you either this is random or it's the output of a pseudo-random computation like this. Tell the difference. Okay, well, the obvious strategy, if you could run forever, would be to brute force every possible key and check. Do I eventually, knowing that these inputs are 0, 1, and 2, do I eventually get an output from this AES encryption that matches the bits you gave me? If the answer is yes, then with high probability, the probability you're going to get that for a random string is negligibly small. So it's overwhelmingly probable that if I can brute force every key and find a key that matches the bits you gave me, then this is not a random string. So basically, if I could run forever, I could attack this. The assumption here is, just like we've talked about before, if the attacker can't run forever, if they can only try a small fraction of the key space, their probability of distinguishing these bits from random is negligibly small. They're not going to be able to distinguish from random. And once we get down to you can't tell the difference between these bits and random bits, all you have to do is say, okay, great, it's just like a one-time pad from there. Right? So that's how we leverage this into a secure system. Right? In fact, what this technique is, this technique of generating a bunch of pseudo-random bits deterministically and XORing with plaintext, is used for all kinds of ciphers. In fact, the problem of building a secure cipher really comes down to the problem of generating these pseudo-random bits. If you've got an algorithm for doing that, and it's good, you've got a way to encrypt arbitrary data. That's why counter mode is such a great illustration. Okay, so counter mode. Now, before we go on from counter mode, how do you decrypt counter mode? If I give you an AES key, and you know that it's going to start from 0, the counter, how do you decrypt it?
You would need the initial nonce and what?
Well, let's just say, for simplification for now, we're starting with 0 as our initial nonce, or our just key state. I'll tell you what nonce I started with. When I encrypt a message for you, I'll say I started at 0, or maybe if it's the 20th message I've encrypted, I'm starting with 5,700 or whatever. But how do we decrypt? Once you know the initial nonce, or the initial counter. It's the same thing. Isn't that cool, right? So first observation, decryption of counter mode is exactly the same algorithm as encryption of counter mode. If you're building a really tiny piece of hardware, that's actually nice because it reduces the amount of stuff you have to build. That's great. Okay, what is the other advantage of that? If you happen to look, just in terms of how much code you have to write, what else do you notice about that? What algorithm are we never using when we implement counter mode?
AES itself.
No, we're using AES. If we're using AES or block cipher, it's there. We're using AES. What's missing?
Block cipher.
Good. Remember, block ciphers consist of 2 algorithms, N cipher and D cipher. In CBC mode, we used them both. Over here in counter mode, we're only using one. Whatever. It saves us some code. That's nice. So hold on. So that's nice too. What about in terms of efficiency?
Parallelization.
Parallelization. Why is this parallelizable?
So It's independent of the previous.
Yeah, every block stands on its own. I mean, if you know where you're going to start in the counter space, you can make 1,000 threads that all go off and encrypt different parts and run on different, cores of your CPU. Very parallelizable, both encryption and decryption. Actually, counter mode is looking really good to me. I like counter mode. It's a very good mode. How do you screw up counter mode? What do you have to do wrong? Assuming your block cipher is secure. How do you screw it up?
If you started back at 0 every time.
Ah, good. If I always start with the same counter, I've got a deterministic encryption scheme. Once again, we know those are always going to be screwed up, right? Because they're deterministic, they can never be semantically secure. Okay, so I need my counter, at least my initial counter for a given message, to always be what?
Random?
Good.
Pseudorandom.
People are saying pseudorandom, people are saying random, people are saying unique. Which? Does it have to be random? I used 0 here. It wasn't random. Unique, right. So actually, let me be a little bit more precise. Let's say that instead of starting at 0, I'm going to start and I'm going to use a value C. Actually, let's not call it C. Sorry about that. Let's call it IV because it really is an IV. It's an initialization vector. Okay, so I'm going to pick an IV of some kind. It may not be random. Might be random. It doesn't have to be. IV plus 0. IV plus 1. And here, by the way, I'm literally doing addition. This is not XOR. IV plus 2, and so on. It's addition, but obviously if we hit the 2 to the 128, if we hit the end of the number of bits we can fit in the block cipher, we'll have to cycle around, but I'm not going to write that out, okay? Okay, so somebody said unique initial IV. Almost right. Although, what happens if I use a unique IV that's is unique at this initial position, but is not going to guarantee that every single block gets a unique value going into the block cipher? Let me be more specific. Let's say I encrypt 2 different messages with IV, and IV plus 1. You would agree these are 2 different unique IVs, initial IVs, great. But let's say the messages are each 2 blocks long. Okay, so I have M0 XOR, let's actually call this M1 XOR enc under K of IV XOR a message. And then I have, sorry, I already did the XOR of the message, sorry about that. And I have M2 XORed with enc under K of IV plus 1, meaning the second block of the message. That's how it's going to be enciphered. Okay, so this is one message. And then I encrypt another message, call it M1 prime and M2 prime. Okay, and this one is going to be enciphered with, let's say, the initialization vector IV plus 1, and this is going to be with the initialization vector IV plus 2. Do we have a problem? Does this even make sense?
M1 prime equals M2?
Yeah, well, yeah, that is definitely something that would happen, right? That could happen. So basically my point is, remember, when we encipher a message that is 10 blocks long under an initialization vector, we're not just worried about the first block, we're worried about all 10 of them. If we reuse a counter in any of those blocks, either across messages, 2 messages overlap and share a counter, even maybe in the last block, bad things can happen. What are the bad things that can happen if I reuse a key string? Now, obviously, let's say I reuse an IV for 2 different messages. We've already talked about how it cannot be semantically secure because it will be deterministic. But is it worse than that? Like, how insecure is it if I reuse my IV across all of my messages? Like we saw with AACS a few minutes ago. Yes?
Because then you could XOR them together and determine the key.
Good. So remember, in the one-time pad, if I'm stupid and I do something like this, P1 XOR K and P2 XOR the same key, we talked about how you could XOR these things together, the keys would cancel out, and this would be equal to P1 XOR P2, which in some cases could be catastrophically bad if people can pry that result apart. All the encryption goes away. In counter mode, the exact same thing will happen to you if you forget to use unique counters in your message. The minute you do something like this, oh, sorry, this is CBC mode, same difference. The minute you do something like this, okay, should have used P2, but whatever. The exact same attack on one-time pads hits. Wham, 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 okay? So big, big deal when people screw this up. And people screw this up all the time. Let me see if I have some examples of people screwing it up. Because I love people screwing things up, okay? Good, so we sort of talked about this. Shoot, I did not. Okay, good. Here is an example. So years ago, Microsoft decided to add encryption to Microsoft Office. They thought it was the coolest idea. They were going to do it. They didn't use counter mode, but they used another stream cipher that for now works enough like counter mode. Let's just say they used counter mode. Right? Every time you encrypted a blob of text in a Microsoft Word document, they would use the same IV. They would encrypt it and write it to a file. Okay, so if you went back and you edited that text, so let's say that the initial version of your text was P1, was literally this thing. It was literally NK of IV XOR M1, and then later you edited your text, thus turning your text into M2, and you saved it to a file, it would still be encrypted with exactly the same IV, which meant that if you had two different versions of that file from different time periods, you could take that text, you could XOR it together, and what would you learn? Well, if I deleted words or I made obvious changes, oftentimes the XOR of two different versions of the file, will actually produce very, very different, very obvious indications of where edits happened. And so it turned out that just by looking at the XOR of those two things, you could figure out what people had edited between two different versions of a file. So people make mistakes like this, and it's really catastrophic and really bad when people reuse initialization vectors. So, summary of counter mode. The IVs must be unique, the counters must be unique through the whole message. Don't have to be random, just have to be unique, but you can really never ever reuse them because terrible things will happen. Okay. So I want to claim to you that both of these modes, under the assumption that these block ciphers are secure, are semantically secure, and I don't need to prove it to you because I will make you prove it later on in the class. All right, so we've talked so far about one aspect of security. And the aspect that we've talked about is, remember at the beginning of discussing this stuff, we said there are two properties that you get from cryptography that you care about on a communication channel. And I hope you guys maybe can dig back and you can tell me what those two properties are. Anyone remember? I don't want you to look for this. Good. What are those two properties? Remember I had the picture of the baby on the slide. And I said a communication channel, you have these active attackers, you might have passive attackers. And in order to protect ourselves against these attackers, crypto provides us with two essential properties. Yeah? Confidentiality you are good at. But I told you don't tell me integrity because it's a little confusing. I want you to use a different word. Yes? Authenticity. Meaning that a message that I receive, I can verify somehow that it is not only the correct message, but what's the meaning of correct? Correct means it actually came, it is the message that the person who sent it intended to send. So that's why we use authenticity. Okay, I hope I have somewhat convinced you that counter mode and CBC mode provide you with the first property, which is confidentiality. I hope I have not convinced you that they provide you with authenticity, because nothing that I've said so far guarantees that. In fact, it turns out that these modes can actually be kind of dangerous if what you care about is authenticity. Let's take counter mode. Okay, so remember, I'm an attacker. What did I do with that eraser? I am an attacker on a communication channel, and I'm an active attacker, which means what? Yeah.
You can mess with whatever's being said.
I can mess with anything I want. Any bit that goes over the message, I can change. Okay, so I am an adversary here. We have sender sending some encrypted messages to a receiver, but the adversary can intercept and tamper with them. And I'm going to use counter mode encryption to encipher those messages or encrypt them. Okay, so let's say, just make it simple, I have M1 XORed with, some count encryption under K of, counter. Let's not worry about what it is. And I'm sending that over the wire. Okay, and A wants to mess with that message. What can they do to that message? The message says, I like pizza, and A wants to change that, so it now says, I want Chinese food. Can A accomplish this on this encrypted message? They can't see the message, it's encrypted. Can they mess with it?
Can they just encrypt a new message and then just send it?
But they don't have the encryption key, right? If A has the encryption key, you're right, we're toast. But we're using a secret encryption key, maybe I should have written that. There is this key K that the sender and the receiver share, but A does not. Yes?
For example, for one iPad, I can XOR the pizza and Chinese food and XOR to the ciphertext.
Good. If I'm A, and I guess that S is probably asking for pizza. I have to guess, I don't know, it's encrypted. But if I guess that, right, I can do the following. I can take any message M1, which has been XORed with some, encrypted counter. I'm not going to write that out. And I can XOR into that my own thing, which I'm going to call, I'm looking for a word here. Just call it V because I like the letter V. Okay? All right, all I'm doing, and sometimes you hear people say this idea of bit flipping. What I can do, thanks to XOR, is I can flip bit. I change the value of a bit in a ciphertext, and that goes over to the receiver, and they decrypt it using counter mode. What's going to happen to the resulting plain text if I just flip one bit?
Gibberish. You get like nonsense.
No, not with counter mode. What's going to happen?
Different message.
What's that?
Different message.
How different?
A little bit.
So remember, I've expressed it this way for a reason. So I have M1, which is the actual message that sender sent, XORed with this thing that only the sender and the receiver can generate, XORed with this V, which the adversary, I remind you, XORed into the ciphertext. Now, when the receiver decrypts, what does the decryption operation do? What is the receiver going to calculate?
M1 XOR.
They're not going to calculate M1. They're going to calculate first this thing, right? The encipherment of the IV, right? They're going to XOR into that this, because remember the decryption algorithm in counter is the same as the encryption algorithm. Okay? They're going to calculate this value, and then in XOR, the magic of XOR, which makes counter mode work, is this will cancel out with this, and the resulting message will be what? Very good. And so V is an arbitrary value chosen by the attacker. Could be zeros, that would mean no change. Could be a single bit, which would mean one bit of the resulting message would change. Or it could literally be the XOR difference between pizza and Chinese food, in which case the decrypted message that the receiver would get would literally say, I want Chinese food. At which point, disaster ensues. This is a really silly example, but it's the kind of thing that could be really disastrous if you actually needed to trust those messages. Now, imagine that M1 is actually the total profit that AT&T made in 2016, and an attacker has access to that file, doesn't actually have the key to read the file, but can XOR arbitrary crap into it. What happens now? Well, that's really bad for AT&T. Maybe you could reduce the value of AT&T stock by a few percent and make a killing doing that kind of thing. So this is the sort of thing that will happen with encryption scheme. It actually really does happen. So what do we learn about counter mode? Counter mode, does it provide authenticity?
No.
Skepticism here. Does it provide authenticity? All by itself, counter mode. Does it provide authenticity?
No.
No, it does not. Because counter mode provides confidentiality if you use it right, but nothing about it prevents an attacker from tweaking arbitrarily the underlying plaintext of the message such that when it's decrypted, that plaintext will come out differently in a very specific way. There's no way the receiver can tell the difference. What about CBC mode? What do you guys think? I'll go back. I'll show you CBC mode. Can the attacker, seeing only the ciphertext and the IV, which I've decided is part of the ciphertext, can they tweak a ciphertext such that the decrypted message will be different, and the receiver can't tell. They can't? Well, to give me your intuition why they can't tweak it.
Plaintext itself is being encrypted too, in this case.
Well, I mean, the plaintext is definitely encrypted, right? So they don't see the plaintext. Let's just make our goal simple. I don't care what the plaintext is. I want to flip a bit. That's all I want to do. Flip one bit of the mess with the message such that one bit of the plaintext will come out different than what was intended to be sent. Yes.
You're flipping bits in the ciphertext, but then it has to go through the decryption.
Okay, so your claim to me is that if I flip a bit in the ciphertext, then when it goes through this decryption process using a key that I don't know, I'm the attacker, the decryption operation kind of will work like a blender. If it's the wrong value, the thing that comes out of it's going to be very different than the thing I put into it. So it'll be kind of like, really like massacring some of the message. How much? If I flip one bit somewhere in the ciphertext and then it gets decrypted, how much of the message will be trashed?
One block?
One block, just one block. Just to reiterate, flipping one bit does not carry through on the decryption operation. It's just one block. Okay, so first question, does the decryptor know that a block got trashed? Yeah, like what does it mean for a block to be trashed, right? Like, do they have a reliable way of telling the difference between a authentic message and a trashed message? I mean, human beings looking at a message could probably tell it was trashed. Like, what if the message was like a binary thing and had some like noisy looking parts anyway, and an attacker messed with some of it and added like one more noisy part? Do you have a reliable way as the decryptor to know that the message was trashed?
Maybe a hash.
Is there any kind of checksum in it?
No.
There's no parity stored anywhere, right?
Right. Okay.
So it's kind of like if you were to spin up 1,000 ledger you were talking about earlier, you could have had the same problem with any of the other ciphers where if something goes wrong in your system, it could be broken because of that just about as easily.
Okay, so I think we're all getting to the basic idea that is, with just CBC mode and no additional checksum kind of operations, you can make changes to the ciphertext such that the plaintext will decrypt differently. So, and there's no built-in way for CBC to check that. You'd have to add something different. Yes?
But you're just sabotaging it at that point, right? You're not changing it to something
Good. So what we've said is it is malleable. Malleable is the word. We can maul the ciphertext and change the resulting plaintext. But if we mess with an arbitrary block of the ciphertext, its malleability is not as precise and powerful as the malleability we got from counter mode, where I can literally change any bit of the message. So when we just mess with ciphertext blocks, we get kind of a destructive, but a limited destructive kind of malleability where we can trash parts of the message. But I want to make a stronger claim to you. I want to claim to you that actually we get a little bit more power than that. CBC is a little bit more usefully malleable than what you just claimed. Okay, I want you to look. Remember I said, been very explicit in CBC mode that the IV has to go over the wire with the rest of the ciphertext blocks because it's part of the ciphertext. You need it to decrypt. What if I don't mess with any blocks of the ciphertext, but I mess with the IV? What happens now?
You mess the whole message.
Really? Look at the decryption algorithm more carefully.
Probably just the first block.
And how? How does it mess with the first block? Does it trash the first block? You think? Look closer.
How much are you changing the IV?
I want to flip one bit of the message in a precise
You're
way.
going to change one bit of the ciphertext.
Good. So our observation here is that the IV never goes into the block cipher operation. And so changing a bit in it is not going to produce this kind of blender effect that we talked about. But it does get XORed down here with this thing that is, almost the plaintext. It's the output of the block cipher. Decryption gets XORed with the IV. And my claim is if I flip one bit of that initialization vector, it will result in a corresponding change to the same bit of the first block of the plaintext. So we have a limited ability to mess with one block, but I'm going to go farther than that. Yes?
So in this case, the attacker is allowed to transmit an incorrect IV, or allowed to.
My only claim here is that the IV is part of the ciphertext. And since I've said that our attacker is allowed to mess with anything in the ciphertext, yeah.
So, but this is an attack at the decryption process, right?
It is an attack that happens here, And you're right that the result of that attack should affect the decryption. Yes?
If only one block is encrypted, you can just write whatever you want.
Ah, good. So in the base case, where the plain text is 1 block long, you can actually edit any block of the message with nothing bad happening to you. Very good. So great. All right. So that actually is a real problem for short messages. For longer messages, it seems like my capabilities are a lot more limited. I can't flip arbitrary bits without trashing block. We missed one thing. Okay. You notice that the initialization vector is used for the first block, but actually in CBC, every block has an initialization vector of some sort. So this second block here, what's its initialization vector?
Ciphertext from the
Right. The first block of the ciphertext serves as the initialization vector. So let's say I want to flip the 23rd bit of the second block of the plaintext. Can I do that with precision? Yes, I can flip a bit here in the first block of ciphertext, and that will flip the 23rd bit of the second block of ciphertext with precision. And yes, there will be some consequence to that, which is that the first block of ciphertext, the first resulting block of plaintext, will be trashed. So I get the ability to trash, I get the ability to precisely edit any bit of the message with the consequence that, with the exception of the first block of the message, I will have some collateral damage to the rest of the message. Turns out that this is still very powerful, and you're going to learn how powerful soon, but you can actually do some really interesting stuff with this ability. Okay? So what we've learned, hopefully, at the end of this, is that none of these modes that I've shown you so far provides any resistance to these malleability attacks. Not only can the messages be basically trashed because there's no built-in checksum, but they can also sometimes be edited in very precise and meaningful ways. And those meaningful ways, depending on your protocol, could actually create really terrible results for your system. Okay. How do we fix this? Well, the answer is we need another primitive. And we need a primitive that provides us with authentication. And this primitive we're going to talk about is called a message authentication code. When you combine this stuff with encryption, you get a combined primitive that's called authenticated encryption. This is the primitive you will actually need if you're in an adversarial environment, not a passive adversary. You have a real active adversary. Okay, so the primitive we need is called a MAC. MAC stands for Message Authentication Code, and message authentication codes do for authenticity what encryption does for confidentiality. A message authentication code, in the general simple case, is actually just one algorithm, which, to make life confusing, we're going to call MAC. And it takes in a key, and it takes in a message. And we're going to say it spits out a value, which for now we're going to call a tag. Usually these are small, fixed size, like 128-bit, maybe 256-bit values. And this is the MAC algorithm. So we need a key for the MAC. So Alice and Bob want to send a message. They agree on a key for this MAC, and they are going to compute the MAC over a message. And now what are they going to send over the wire? Forget about encryption. We just want to do authenticity now. What do they send over the wire?
The ciphertext add the tag.
Yeah, or in this case, since we're not even bothering to encrypt, we're just going to send the message we wanted to authenticate and the tag over the wire. Good. So Alice sends this. Now what is Bob, when Bob receives this message, how is Bob going to verify that there was no tampering? Good. Yes. So Bob is now going to compute exactly the same MAC using the shared key. Or let's say that it gets M, and then is going to basically do a comparison with this value T that was received over the wire. If the comparison succeeds, we say that the message is authentic. If the comparison fails, we say that something went wrong. We reject the message. This doesn't let us fix the message, but it does let us detect adversarial tampering. Okay? So this is basically the idea. All right? Okay, so fine. We have just shown kind of how a MAC works. Now remember, MACs are not hash functions. They can be built from hash functions, but hash functions, which we'll talk about soon, are not keyed functions. MACs always have a secret key that goes into it. That's what prevents the attacker, who's on the wire, from computing a new tag that would be a fix-up tag. So it has to be a keyed function. Okay, so we have to do this basic thing. All right, MACs. That's all a MAC is. Any question about MACs? Very good. By the way, I have pointed out here that in order to check the message, in most MAC schemes, you simply recompute the MAC algorithm on the same message. What does that imply about MACs? This kind of MAC. Are they randomized? Are they probabilistic algorithms? They're deterministic. For this to work, the MAC algorithm has to be deterministic. This has some implications we'll talk about in a second. Okay, great. So MACs. If a MAC is secure, basically we want to say that to an attacker who does not know the key, it should be very hard to generate a new message and a new tag, because they can edit the tag too, that satisfies this check. That is the guarantee that MACs provide. So the question we should be asking now is, knowing all of this knowledge that we have about, let me come back to that. Oops, sorry. Knowing everything we know about MACs, what do we do in order to combine them with encryption? Okay. So let's say we have a secure encryption scheme, and let's say, just for simplicity, I don't know, it's CBC mode or something, which we've proven is a secure encryption scheme. I'm trying to turn this off. And let's say we have a secure MAC, and I haven't really given you a formal definition of what that means, but let's just say it's hard for an attacker to mess with it. Okay? How do I combine MACs with encryption to get a secure scheme that gives me both confidentiality and authenticity? I'm going to give you 3 proposals, and I will leave you to think about which one is secure. Okay, so we have an encryption algorithm here. And for simplicity, I'm going to assume we actually have 2 separate keys, just so we don't end up using the same key for both. Okay, so we have both parties share keys. Proposal 1 looks like this. Okay, so first, we encrypt under K1 the message M, and then we concatenate, that means concatenation, MAC under K2 of the message. Look good? Seem like a pretty good idea? Okay, good. All right, number 2, possibility. We encrypt under K1 the message concatenated with the MAC under K2 of the message. Okay, so these things are both going into the encryption scheme.
The MAC is taken on the plain text?
The MAC is taken on the plain text, and the MAC itself is shoved into the encryption algorithm. Yeah. Okay, and the third, I'm going to try to make this clear. So I'm going to say we compute the ciphertext C is the encryption, under K1 of the message, and we concatenate to that the MAC under K2 of C, just because it's a little easier to write that. So which one of these is secure? Before you guys leave today, I want you to think about this for 1 minute, and then I want to see a show of hands for 1, 2, and 3. So I'm going to give you 30 seconds to think about this while I erase the board. I'm actually going to give these names just for simplicity, because I think 1, 2, and 3 suck. So let's call this encrypt and MAC. Let's call this MAC, then encrypt. And let's call this one encrypt. I always get these confused. Then encrypt and MAC. Sorry, let's see. Encrypt. Is this? Yes. Then. Okay. These are my nicknames, but these are actually common nicknames. All right. Who likes encrypt and MAC? Number 1. Hands. Anyone want to give me a reason you don't like it? Yes.
Chosen plain text.
Okay. Explain. What's the problem?
If you give them a message, then you know what the MAC of that message is.
Ah, good. MACs are deterministic. We just talked about that. And since they're a deterministic function of the message, seems like that could be a problem for semantic security. I'll let you guys decide if you agree with that later. But that's good. Okay, good objection. How about 2? What's wrong with 2? Yeah.
No way of knowing if the message was trashed or altered anywhere.
Oh, but you can check the MAC when you decrypt it. You'll peel off the encryption. You'll verify that the MAC on the plain text inside is
Still
good.
wouldn't know if the original message was directly changed or not.
But I'm still claiming that the decryption algorithm of this would peel off the encryption would check the MAC, and that seems to do a pretty good job of that. Does anyone feel good about 2? Hands? Okay. Don't worry, I'm not gonna like judge you guys horribly and like you reduce your grade to 0 or anything over this. Okay, good. Hands on 3. Who likes encrypt then MAC? Anyone give me an idea why? There's no right answer to this. I'm just curious.
You can tell if the ciphertext was messed with without decryption.
Ah, I like that. Good answer. That is a good answer. Okay, we're going to leave this great mystery until next time, and we'll talk about it on Wednesday.